for now. So um, we can get it started while waiting for more people to join us. Welcome everyone. Today marks the 50th ECS and Cloud Feedback Symposium. And we would like to take the opportunity to thank everyone here to be part of this growing community. It's exciting, and we are looking forward to our second 50s. So, as usual, we will have three AGU style talks today. And here we feature three early career scientists, Ben and Joonsuk and Peidong. Welcome. And as usual, if you have questions, any questions and comments are welcome anytime in the chat. But if you prefer to ask questions verbally, please raise your hand and we will call you. And if you're interested in sharing your work, please contact our community, which is listed here. And you can find all the information about the context and also the recordings of all the past talks on our ECS symposium. So without further ado, oh, sorry, one more thing before we start. And
With
Andrew has two more announcements.
yeah, with
Go
some
ahead.
further ado. Um, yeah. So speaking of things that are related to 50, so we just had this is the 50th virtual symposium, and we are about to in 2 weeks kick off a 50-hour live stream. So many of you in this community took part in the 100-hour live stream that we had last year, which was US based weather and climate scientists coming together to communicate our science to the public and get them to call their representatives and tell them to protect that science in the face of cuts by the administration. And the cuts are back this year, but so are we. We have many amazing speakers who are already signed up. We're going to start at 4 p.m. Eastern time on June 1st and run through till June 3rd. We have speaker slots free. We would love to have more speakers from this community. So if you're based in the US and are excited about speaking to the public about your work, then please go to wclivestream.com/speak and you can fill out your details there. We'll be in touch. We also have a walk from New York to DC, which is starting in 1 week with some really amazing scientists who are going to be walking this route to deliver letters of support for science to Congress. And then one more update is many of you will probably be going to the CFMIP conference in Taiwan this year. When you apply for that conference, there's the option to also sign up for a mini workshop on state-dependent climate forcing, recovery, and response. State dependence is something that is really kind of like a bugbear in our field. It's like something that we all know is a possibility, but it's something that was poorly understood. So I think it's really exciting that Jonah and Ivan and Zhang Zhu and others are putting together this workshop. So just an advert for that. And yeah, please consider attending this workshop if you're going to CFMIP. All right, I'm done.
Well, yeah. So our first talk speaker will be Ben. Ben, if you like, please go ahead, share your screen.
Okay. Let's find it. All right, can we see this?
Yep, looks good.
Okay, so my name is Ben. I am a postdoc working with Maria Rugenstein at Colorado State University. And I'm going to talk about large-scale trends that are observed over recent decades and argue that land-sea contrast is an important mechanism driving these trends. Oh, it's not letting me skip. Oh, there we go. Okay. Did it move for you?
Yeah, it looks good.
Okay. So the basic motivation of this is there's this very well-known trend. It's kind of a hot topic in climate science right now, this negative interdecadal Pacific oscillation, or often referred to as La Nina-like trend in the Pacific, over recent decades. And what I mean by this is, if you look at the relative sea surface temperature trends compared to the global mean, you can see that the East Pacific has, overall warmed less fast than the West Pacific. And along with that, you have the sea level pressure trend that kind of resembles the La Nina teleconnection, where you have these increases in sea level pressure straddling the low latitude Pacific, and also this decline in sea level pressure over the Indian Ocean relative to the Central Pacific. And so why this has gotten so much attention is that climate models really struggle to capture this trend. So I will show you later that they actually do faintly capture the spatial pattern that you see here, but the magnitude is way too weak in the climate models. And it's only a very select few that capture this, which is sort of suggesting that the models are actually doing something wrong in the observed trend. So we really need to figure out what is driving this trend and why the climate models are getting it wrong. And so I'm going to argue that land-sea warming contrast is an important driver of this trend and trends more broadly. So why I suspect land-sea warming contrast is important. So just for perspective, first I'll show you the sea surface temperature trend pattern. So it's known that this sea surface temperature trend pattern alters the atmospheric circulation and precipitation trends. You can test this in AMIF experiments where you impose these trends. But if we instead look at surface temperature trends, you can see that actually a very dominant pattern in the surface warming is that the land has warmed much more than the surrounding ocean. So if you area weight average between 7 degrees north and south, you end up with a land sea warming ratio of about 2.4. So the land is warmed about 2.4 times as fast as the ocean. And here's showing the sea level pressure trends again. You can expect from first dynamics principles that this kind of a warming pattern should have some effect on the atmospheric circulation. And another reason, this was sort of like a first reason I got into this about a year ago, is I had this series of climate model experiments from my PhD. And essentially, you're seeing what happens when you make the land surface darker in a climate model. It's actually the reverse of this. You're comparing the baseline control to a raised land albedo experiment, and we're keeping the sea surface temperatures fixed. So we're basically isolating what happens when you heat the land and keep the ocean the same. And what you end up with is a pretty similar response in terms of spatial pattern as you see in the observed trends since 1979. Of course, you get this warming of land relative to ocean. And you can see, although the actual amount is not exactly the same, the spatial pattern of it is qualitatively very similar. So in particular, if you focus on the Pacific Basin, you can see that actually when you heat the land and keep the ocean the same, in this idealized set of experiments, you end up with this negative IPO-like or La Nina-like trend that kind of resembles the observed trend. So this increase in sea level pressure in the extratropical Pacific, and increase in sea level pressure over the Pacific more broadly compared to the Indian Ocean. So heating land in idealized model experiments is able to reproduce this kind of negative IPO-like trend in the Pacific Basin. And given the dominance of this land sea warming pattern, it's reasonable to suspect that maybe this is playing an important role in driving this trend. And so why do this? So this is generally not recognized as an important mechanism shaping trends over the Pacific Basin until very recently. And so this is a very good paper that summarizes the existing work on the subject. And you can see that there's all these different mechanisms that are proposed to describe the evolution of the Pacific Basin, things as subtle as rainfall-induced freshwater forcing, but yet the land sea warming pattern, which is a very dominant pattern in the observed trends, is not known to be an important driver of this. So we just really wanted to bring attention to this possibility. So some basics of land sea contrasts. I'll start with the disclaimer that this is really like a big oversimplification of what actually goes on. I could go on all day about the various factors that shape this. But the general idea is you can think of like a first order forcing mechanism as if you heat the land relative to the ocean, right, the warmer air is less dense than the cooler air surrounding it. And so this, increases the thickness between pressure levels. And so, if you increase the pressure aloft, you tend to induce divergence. And so if you remove air mass from the column, you tend to get lower sea level pressure at the surface. So, dynamics aside, the overall tendency is that if you heat the land relative to the ocean, all else equal, the sea level pressure tends to decline over the land surface compared to the ocean. And you can see this in the seasonal cycle. So here I'm showing the boreal summer minus winter surface temperature change at the top, and sea level pressure at the bottom. And what you can see is that as you transition into the northern hemisphere summer, right, the land surface warms much more than the surrounding ocean. You can see that over Asia and North America. And along with that, a first order description of the sea level pressure change is that the sea level pressure declines over the faster warming land compared to the ocean. And this doesn't line up exactly, but to a first order, this is a very important process going on. And you can, of course, see the reverse in the southern hemisphere as you go into their cold season. And so I want you to note this pattern in the North Pacific. You can see that seasonally, this increase in sea level pressure, where the ocean is not warming as fast as surrounding land, that actually shares many characteristics with the observed trend, which I'll show in a sec. Um, so now let's look at the observed trends in more detail and the model trends as well. So we'll start with the model trends. The reason is, even if the models are not totally accurate, you're averaging many different ensembles. And so you're basically averaging out the internal variability, and you can see the pure force response as predicted from the climate models. And what you can see is, of course, we have this very dominant pattern where the land warms faster than the surrounding ocean. And if you look at the shape of this warming pattern, you can actually see that where the sea level pressure declines, that's the blue colors, really matches the outline of where the land is warming faster than the ocean. And you can see this, to a smaller extent over the southern hemispheric continents, for example, South America, there's a relative minimum. Um, and so really this land-sea contrast pattern is very important in the model trends. So what the model thinks the force response should be, land-sea contrast is a very important factor. And if we go to the observed trends, of course, they're more noisy than the CMIP6 mean, which is to be expected. But overall, you see many characteristics that resemble the model trends. So you can see, of course, this land-sea warming pattern. And like I said, it's more noisy, but you do see, for example, this decline in sea level pressure over Northern Africa and kind of a minimum over the interior of Asia and kind of extending into North America. You can actually see that a lot of the features that the climate model, predicts, even though the magnitude might be off, are similar to those in the climate model or the observations. So you can actually see over the Pacific that there is this very faint negative IPO-like trend. The sea surface temperatures have warmed a little bit more in the East Pacific compared to the West, but more broadly speaking, you can see these kind of tongues of solar warming kind of match similar to the location as they do in the observed trend. And as well as you get this very slight increase in sea level pressure over the extratropical Pacific. So very faintly captures this trend. And what's interesting, if you compare globally, the warming pattern is in CMIP6, the land sea warming ratio is about 1.79, but in ERA 5, it's 2.4. So the climate models strongly underestimate the land sea warming ratio. And to get an idea for how extreme this is, if we go to abrupt 4 times CO2 experiments, so we're instantly quadrupling carbon dioxide. If you go to the first 3 years after you do that and compare that to before you did that, so what is the change in response to the abrupt quadrupling of carbon dioxide? If you look at the first 3 years versus control, the land sea warming ratio is 2.49. So that's comparable to the observed trend. So you need a very extreme forcing situation to recreate the observed land sea warming ratio. Um, and the idea is that, given this land sea warming pattern and the negative IPO-like trend that the models predict in the Pacific, maybe the inability of models to capture the magnitude of this is related to their underestimation of the land sea warming ratio. So now what's interesting is if you look at the 4 times CO2 experiments, now I'm going to show the spatial pattern. So the observed trends again are at the top, and the abrupt 4 times CO2 first 3 years versus control is at the bottom. And so it's interesting, in the abrupt 4 times CO2, over this period where you have a very similar land sea warming ratio as in the observed trends, you can see now that the spatial pattern over the Pacific matches up very nicely with the observed trends. It's not perfect, but you can see that you get these increases in sea level pressure over the extratropical Pacific. The magnitude and spatial pattern of it is pretty similar. You can also see, for example, this increase in sea level pressure over the Pacific relative to the Indian Ocean. Um, if you look at the surface temperature pattern, you can see that the sort of magnitude and shape of these flanks of slower warming in the East Pacific really match up quite nicely. The similarity of these two, which occurs in, when you have a similar land sea warming ratio, is suggesting that maybe, this negative IPO-like trend in the Pacific is related to the land sea warming contrast. And maybe climate models, they underestimate the land sea warming ratio. They do faintly capture this pattern, but it's not strong enough. And so maybe their underestimation of the land sea warming ratio is why they're not able to reproduce the magnitude of this trend. Um, and if you remember about a month ago, Moritz Gunther's work, which is very good, by the way, you should check it out. They found that if you increase CO2, if you quadruple CO2 instantaneously over ocean only, you actually end up with a more El Nino-like response over the Pacific, which suggests that the land-sea contrast is really a very dominant driver of this early response in the abrupt 4 times CO2 experiments. And I won't go too much into this, but I thought it was also interesting that the GPCP precipitation trends, which are kind of independent from the EAR5 reanalysis based on satellite observations and station data, the precipitation pattern is also pretty similar to the abrupt 4 times CO2 early response. You can see, for example, over Asia and the far western Pacific and Indian Ocean, this increase is kind of similar to what you get in the abrupt 4 times CO2. So what's the implication of this? So if our theory is correct that the land sea warming ratio discrepancy, so the underestimation of the land sea warming ratio by climate models is accounting for some of the discrepancies with other observed trends, then you might be able to constrain projections by figuring out why the models underestimate the land sea warming ratio. So what I mean is that, if you determine the mechanism might say something about whether this issue will persist or decay with time. So for instance, one possibility is that the climate models underestimate the ocean heat uptake. And so if this was true, assuming you're not constantly increasing the forcing, this should eventually decay in the long term. But, if you have it due to actually land moisture availability for evaporation, so the sensible to latent heat flux partition over land, then there is potential for the land sea warming ratio discrepancy to persist with time. And so if the mechanism suggests that the underestimation of the land sea warming ratio by climate models will persist, um, then it brings doubt to this long-term positive IPO-like or El Nino-like projection that the climate models give, which has major implications for both regional climate and global climate sensitivity. So I won't go too much into these conclusions right now. All the figures I showed, I have in this one big figure that I'm showing in the paper that I will hopefully be submitting very soon. And the basic idea is that all these maps on the left, these are all showing fields of surface temperature, look pretty similar to each other. The observed trends are in the middle here. The CMIS6 trends here and the abrupt 4 times CO2 in the bottom. And the sea level pressure on the right, these as well all look pretty similar. So this is suggesting that the land-sea warming contrast is a very important driver of global trends, including those over the Pacific Basin. And you can contact me at this email with any questions or suggestions. Thank you.
Thanks, Ben. It's really nice. Any questions? Mm, Question.
Yeah, if you do have time, then a quick one. Well, great talk. Something which, I have been thinking for a while, probably not the only one. Great seeing it let out so nicely. Two things I wonder, a quick one, the 1, 2 years in the 4 times CO2, would that still hold if you go to, say, 5 years? Or is it really just this transient change, which is the quick response?
Yeah, so like basically, some of the features that you see, like the land sea contrast features, actually hold even in the equilibrium. the land actually warms more in the equilibrium due to the sensible to latent heat flux partition. The reason I did like years 1 through 3 is if you go longer than that, years 1 through 4, the ocean warming kind of catches up, and so the land sea warming ratio actually becomes less than the observed trend. So you will see a similar pattern, but it kind of, it doesn't really hold, particularly over the North Pacific. This sort of does decay over time. It kind of ends up looking different as you go longer.
Yeah, great stuff. And real quick, maybe a comment. So I did look at spring and summer temperatures, and what you see is like this huge MSLP reduction over the Arctic. And then you have to have, for simple mass balance reason, higher pressure around it. And yeah, that might also play a role dynamically, I suppose, which is also kind
Right.
of a different or various form of land-sea contrast.
Right. Thank you.
Thanks.
So Joonsuk?
Just had a quick question before I start talking about my project. So, have you looked at the contributions of aerosol forcings in the
No,
land sea
so
constraints? Yeah.
so one caveat is I haven't really like isolated the individual forcing mechanisms behind that. So this is sort of just like the net effect of the forcing. So what exactly drives it, in terms of individual mechanisms like aerosols, greenhouse gases, I'm not sure. And I guess it is noteworthy that the abrupt 4 times CO2, here it is, sort of recreates a very similar pattern as you see in the observed trend. And, the increase in CO2 is the only thing that's going on there.
Yeah.
Yeah, no, I would expect aerosols to definitely have a role here.
Yeah, just wondered because they're very land-based forces. So, thank you.
Thank you.
Great. So if you have any follow-up questions for Ben, please put them in the chat. Thanks, Ben, once again. And next we will have a Joonsuk. Joonsuk is already here, ready for the talk. Yeah, please go ahead.
All right. Shoot. Can we all see the slides?
Yep, that's good.
All right. Hi, everyone. I am Joonsuk. I'm a postdoc at Columbia University. Thank you for having me. Thank you for coming here. I'll talk about robust impact of tropical Pacific SST trends on global and regional circulation in boreal winter. And this is a project joint first authored by myself and Ridian Thomas, who is also a postdoc at University of Reading. And we worked on this project about a year ago when we were both PhD students in our previous institutions with our advisors, Nick, Tiffany, and Tim. So I don't need a big introduction for this slide. So we all know that the tropical Pacific sea surface temperature trends are showing observation model trend discrepancy. And in the observations, we see more warming in the Western Pacific and less warming or relative cooling in the Eastern Pacific. So this pattern is all often described as La Nina-like, and also in the coupled climate models, and most of them simulate an El Nino-like SST trend where we see more warming towards the Eastern Pacific. And there has been many studies working on how these different SST trends and patterns impact the global mean surface temperature, radiative budgets, or energy balance. But recently, we also found out that it also impacts the atmospheric circulation. So for example, I am sharing a figure here from our previous paper where we see a huge difference in circulation trends in the Southern Hemisphere winter because of this different SST trends. So in the top, I am showing you the Southern Hemisphere circulation trends in a climate model simulation where the SST trend is like El Nino. And the bottom, I am showing you Southern Hemisphere circulation trends in the simulation where the sea surface temperature trends are like La Nina. And we can see that there are large changes, large differences in this Southern Hemisphere winter circulation, particularly over the South Pacific. So this told us that the tropical Pacific SST trend discrepancy can impact the circulations in Southern Hemisphere
and during Southern Hemisphere winter. But we wanted to extend this to other seasons and to other hemisphere. And particularly, we wanted to focus on the boreal winter. And first, because it's the season where it is known to be very ENSO sensitive. And also there are emerging trends in boreal winter. For example, the figure here I am showing you are the trends in the zonal mean zonal winds during DJF, where we see jets shifting poleward. For example, it's indicated by the red colors on the polar flanks of the jets and blue colors in the equatorward flanks of the jets, and we see the jets are shifting poleward. So we wanted to understand how the tropical Pacific SST trends are contributing to these emerging circulation trends in boreal winter. So the two big questions we try to answer in this talk is, what are the robust impacts of La Nina-like SST trends on the circulation during boreal winter? And second, how does constraining coupled model tropical Pacific SST trends to observations improve the simulated trends in the coupled models? So we're going to answer this question using two different methods. First, I'm going to use the hindcast conditioning method. So in the hindcast conditioning method, we are using a hindcast simulation initialized every November. And we have 40 members of this hindcast simulations, and it's run for 17 months. But in the following DJF, so month 14 to 16, there will be a large spread in their SSTs in the tropical Pacific. And we repeat this for 38 years. And when we can select every member, randomly select each member every year and create a synthetic 30-year, 8-year trend member. And so we created 10,000 of these 38-year trend members, and we selected top 0.5% or 50 trend members with the best tropical Pacific SST trends. And I have to tell you that this was done using the HeadGem model, and that 50 member was considered as the Pacific conditioned ensemble. And the rest is considered as the non-conditioned ensemble. So this is the first method we will use. And the second method we will use is the pacemaking method. So pacemaking refers to constraining SSTs in the coupled model simulations to observations in the targeted region. And for this purpose, we'll use the Pacific pacemaker experiments from the CSM2, and we're going to compare this with the CSM2 large ensemble simulations, which is free running couple simulation, and we're going to call this the non-pacemaker ensemble. So we are using very different two methods applied to two different models, and we will quantify the difference between the Pacific ensemble and the non-Pacific ensembles, and we will try to focus on the robust features that emerge from these two different methods applied to different models. So before we look at how the circulations are different in these two sets of ensembles, I will go quickly introduce how these methods are doing in constraining the tropical Pacific SST trends to observations. So on the left, I am showing you the DJF sea surface temperature trends in the non-conditioned ensemble and the non-pacemaker ensemble. And as we could all expect, we are seeing more warming towards the Eastern Pacific, just like as many other coupled climate models, and which is different from the observed SST trends on the right. But when we apply these two methods to this coupled climate model system, we find that they are capable of simulating the observed SST trends. So for the Pacific condition ensemble in the top and the Pacific pacemakers in the bottom, they all capture the SST trends in the observation. So this tells us that we can use these methods to understand the impacts of tropical Pacific SST trend discrepancy on the circulation. So now I will walk you through how the circulation trends look different between the Pacific and the non-Pacific ensembles. So here I am showing you first the zonal mean temperature and the zonal wind trend differences between the Pacific condition ensemble and the non-condition ensemble. So this is the impact of tropical Pacific SST trends using the hindcast conditioning methods. And we can spot a few features such as tropical cooling and also weakened subtropical jets indicated by the green colors, and also northern hemisphere cooling trends, and also a polar shift of the mid-latitude jets. And similar features emerge when we look at the pacemaking method. This is the difference between the Pacific pacemakers and the non-pacemakers. We see similarly tropical cooling and also weaker subtropical jets, northern hemisphere cooling, and also polar shift of the mid-latitude jets. And interestingly, these features all resemble the interannual response to ENSO. So in the bottom, I am showing you the La Nina minus El Nino composite from reanalysis data, and we can see that they resemble the responses to tropical Pacific SST trend discrepancy in the upper panels. So for example, we also see tropical cooling and weakened subtropical jets, and also polar shift of the mid-latitude jets and the northern hemisphere cooling. So we looked at the circulation patterns regionally, and we can see here I am showing you a similar layout as the previous figure, but it's for the upper tropospheric zonal wind at the 200 hectopascals, and the sea level pressure. And so in the first row, we can see that the wind responses that we saw in the previous slides is dominated by the signals in the Eastern Pacific, where we see strengthening of the Walker cell and weakening of the subtropical jets, and as well as strengthening of the jets in the more polar latitudes. And in the sea level pressure pattern, we also see positive sea level pressure trends over Aleutian Low and also North Atlantic, and which resembles the Pacific North American pattern, which we expect to see during El Nino and La Nina years. And following these changes in the circulation, it also has effects on the surface impacts. So for example, here I am showing you the surface air temperature and precipitation, and we can see that the La Nina-like SST trends lead to cooling in many regions around the globe, and especially in ENSO-sensitive regions. For example, these regions include where I marked in the blue boxes, such as North America and also Southern Africa and tropical South America. And similar things happen to the precipitation. We see robust precipitation responses over the Gulf Coast or the maritime continents and South Africa, and those regions are where the La Nina impacts the precipitation or derives anomalous drying or wetting responses. So these suggest that there are robust responses to tropical Pacific SST trends emerging in our two different methods, and it also tells that it resembles the interannual response to ENSO, and this means that the interannual teleconnection theory connecting the ENSO and remote circulation and surface impacts are useful for also understanding the impacts of tropical Pacific SST trends and related surface impacts. So far I have talked about the impacts of tropical Pacific SST trends, but in the remaining time, I'll talk about how it has connections to the observed trends, or how it improves the simulated trends in the coupled models. So here we are revisiting the zonal wind or the jet trends in the reanalysis. Here I am showing you the 500 hectopascal zonal wind trends in the reanalysis, and we can see a polar shift indicated by dipole of zonal wind trends. So we see in the darker gray colors regions, we see positive trends, and more equatorward side, we see negative trends, indicating the polar shift of the jets. And we're going to quantify the polar shift by taking the difference between the darker gray and the lighter gray boxes. And when we do this for reanalysis and the Pacific and the non-Pacific ensembles, we find that the Pacific ensembles simulate more polar shifted jet than the non-Pacific ensembles. There are a large spread between the ensemble, across the ensemble members, and also there are some uncertainties, but overall, the tropical Pacific SST trends contribute about 1/3 of the jet shift in the models in the ensemble mean. Also, we wanted to see how the simulated surface impacts are improved when we constrain the tropical Pacific SST to the observations. So here I am showing you the DJF surface air temperature trends, and the blue boxes here are the regions where we find robust impacts from the tropical Pacific SSTs. And you see that in these blue boxes, the warming is relatively muted compared to the other regions, or they exhibit cooling in some regions. And for example, this is if you take the North American box here, the observed trends are in black horizontal lines, which is a muted warming. However, the non-Pacific ensembles or the pink box and whiskers simulate greater trends than the reanalysis in most cases. And for example, the non-pacemaker ensemble, which is on the right, does not capture at all the observed trends. However, when we constrain these models to capture the tropical Pacific SST trends, they simulated cooler trends, and the agreement between these couple simulations and the observations are increased. And similar picture appears in different regions in the blue boxes where constraining the tropical Pacific SST leads to cooler surface air temperature trends, and therefore the agreement between these couple models and the reanalysis are increased, as we can see with the cyan box and whiskers and the black horizontal bars, which is the reanalysis. So to summarize, we have used two different methods, Heinkes conditioning and pacemaking, to constrain tropical Pacific SST trends to observations in the coupled climate model system. And by doing so, we quantify the robust impacts of tropical Pacific SST trends on the circulations, which resembles the interannual response to La Nina. And when the tropical Pacific SST trends are constrained to observations, the surface impacts are improved. The simulated surface impact trends are improved in the coupled models. So if you're curious for more details in these methods or more results, we have a paper out last year in MPJ, or you could ask me questions now. Thank you.
Thanks, Joonsuk. It was a real nice talk. Any questions for Joonsuk?
I have a
Yes,
question.
sir.
So
Go
this is kind
ahead.
of a philosophical question. Nice talk, by the way.
Thank
So I've
you.
seen some critiques in the literature of calling these patterns La Nina-like. Do you think that this, because it's decadal and it's not interannual, so do you think this kind of puts that to rest, or would you say that La Nina-like is an appropriate terminology for these kind of like 40-year trends?
Yeah, good questions. I think in terms of if we just look at the surface and how it looks and how it interacts with the atmospheric circulation, it seems like just from the impacts on the atmospheric circulation, we can say that it's La Nina-like, but I think how the SSTs are driven and things like that, the mechanism in the ocean might be different from La Nina. So if we were just concerned about the impacts on the atmosphere, I think our results say that to a degree, it's okay to understand it as a La Nina-like atmospheric circulation response.
Cool. Thank you.
All right. Since we only have 20 minutes left, if you have some more questions for Joonsuk, please put type them in the chat. And we're gonna move on to our last talk today, which is Peidong, right?
Can you see my share screen?
Yep,
Yeah, yeah. Thank you
that's
very
good.
much. Yeah. Thank you so much for inviting me here. And today I'm going to talk about Antarctica ozone loss shapes surface cooling pattern and climate sensitivity. And my name is Peidong. I'm a postdoc working with Noah Diefenbaugh at Stanford. So you see this figure many times today. We have this unexpected SST cooling over the past 4 decades, mainly in the Southern Ocean and Eastern Tropical Pacific Ocean. But state-of-the-art climate models are unable to reproduce these observed cooling on average. And the reason behind these regional cooling still remains a subject of ongoing debate. And it's important to understand the SST pattern because the spatial pattern of SST can also have a profound impact on Earth's energy budget. So under the 4 times CO2 experiment, in a model which do not have the observed SST pattern, they suggest a lambda around -1 watts per meter squared per Kelvin, which is in a higher sensitivity climate. But if we prescribe the model with the observed SST pattern, it generally suggests a lambda around -2 watts per meter squared per Kelvin, suggesting a lower sensitivity climate. And the difference here is characterizing the SST pattern effect. So the spatial pattern of the observed SST from 1980 to 2010 has contributed to a more negative lambda or more stable climate by 1.2 watts per meter squared per Kelvin. And it's important to understand what is driving the observed SST pattern, and will the cooling persist in the future or not. This will be important to understand historical climate change and also make accurate future climate projections. The Antarctic ozone has been proposed as a potential driver of the observed cooling by Dennis Hartmann in 2022. The mechanism is that we have this decreasing Antarctica ozone, and this is leading to an increase in the southern annular mode. Here, the SAM is inverted. So the SAM is the dominant mode of variability in the southern hemisphere. During the positive phase of the SAM, it characterizes a poleward shift in the westerly jet. And when we have this poleward shift in the mid-latitude jet, it can lead to a enhanced equatorward ocean heat transport due to Ekman circulation. And this will going to lead to a cooling Southern Ocean SST. So here's demonstrating the mechanisms of how Antarctica ozone depletion could drive a cooling Southern Ocean SST through the wind-driven ocean circulation. And recent modeling studies by running these all forcing but ozone and running all the forcings including ozone have found that the ozone's contribution does contribute to a cooling in the eastern tropical Pacific Ocean and maybe some of the cooling in the southern ocean in the Pacific sector as well. But the magnitude of this ozone-driven cooling is too weak comparing to the observed SST. So here the cooling can be maybe around 1 order of magnitude smaller comparing to the observed cooling. So suggesting that maybe ozone's role is too weak to explain the observed SST. But the problem is that our current understanding of how Antarctica ozone drives the Southern Ocean SST change is mainly through a 2 timescale process. On the short time scale, this is what I discussed earlier. We have this enhanced surface westerly wind, and due to the Coriolis force, it will lead to this equatorward Ekman transport, and this will cool the sea surface temperature. And this is a rapid time scale on the order of years. But on a longer time scale, when we have this in equatorward Ekman transport, it will also slowly lead to a deep ocean upwelling, and this will indeed warm the sea surface temperature on the order of decades. And this is the schematic based on the coarse resolution climate model simulations, where the ocean resolution can be around 100 kilometers, and these do not resolve mesoscale ocean eddies. And some of the recent high resolution and eddy resolving models, which with a horizontal resolution about 10 kilometers, what they found is that this long time scale warming response can be much reduced or largely muted. And the reason is that when we enhance the mean flow of the upwelling, it can also lead to an enhanced eddy circulation that is counteracting with itself. And this is a process known as the eddy composition. So this long time scale warming response can be more uncertain. And we do have enough observations to verify the short time scale response, but we do not have enough observations to verify whether there is a long time scale warming response or what's the magnitude of this long time scale warming response. And from the contrasting high resolution and low resolution models, we find this process can be very uncertain. So what if we just consider the robust short time scale response and we assume that the long time scale response is small enough due to the eddy composition? How will ozone contribute to a southern ocean SST? So this can be viewed as a upper limit of ozone's contribution to the southern ocean SST. So in order to capture this intrinsic short time scale ozone and SST relationship, we constructed this multiple linear regression model by considering Antarctica total column ozone from the previous year in September to December. And we also considered the isotelic connections and their impact on global SST. And all of these combined to predict annual mean SST in the preceding year. And we learn this intrinsic ozone and SST relationship based on 8 SIMUP6 models from their PI control run. So all of these models we consider incorporates interactive stratospheric ozone. So their ozone fields and the dynamical fields are consistently coupled with each other. And all of these models are using their pre-industrial control run, so we do not need to take care of the evolving external forcing. So it's just captured the intrinsic variability between ozone and SST. And here is the multi-model mean partial regression coefficient based on the 8 SIMUP6 models. So the red color here indicates where their ozone depletion can lead to an SST cooling over this region. So now we can apply this intrinsic ozone and SST relationship we learned from these models and apply to the real-world ozone to see how it explains the real-world SST. So here is the observed ozone time series. It's being smooth. So we can see a rapid ozone depletion period before 2000 and a slowly ozone recovery after the 2000. So the map here shows the observed SST trend from 1979 to 2024 on the left. And the map on the right shows this ozone-explained SST from our regression model over the same period. And the dashed region here indicate where all of 8 SIMUP6 models agree on the sign of the response. So this region has a very high model agreement that suggests a robust response of SST in response to Antarctic ozone changes. So we can see that this cooling pattern matches with the observed cooling spatial pattern remarkably well, and the magnitude is also similar. So this could be suggesting that ozone's contribution can play a substantial role in explaining the observed SST. But the observed SST here does consider greenhouse gases, consider ozone, and other external forcings and internal variability. So it does not represent an apple-to-apple comparison between the two, but it does show that the ozone-explained SST can produce a cooling magnitude that is on the similar order comparing to the observed SST cooling. And here the blue line is the SST time series from our regression model averaged over this dashed region. So we can see a rapid cooling before 2000 and a pause of this cooling after the 2000s. And the 3 different black lines are from 3 widely used SST reanalysis, and they are generally within the uncertainty range from our regression model. So now we can also try to estimate the ozone's contribution of SST pattern effect and their influence on the global climate feedback. So here we use the Green's functions approach to do that. And these Green's functions have been run by these atmospheric general circulation models by prescribing SST over different patches and look at the global response in the global mean net top of atmosphere radiation and the global mean surface temperature. And we can convolve these Green's functions with the SST patterns and to calculate lambda. And we do this with 2 types of SST patterns. One is directly from observations. So this can include all the real-world external forcings and internal variability. We also convolve with the SST pattern with the observations, but with the ozone-explained component removed. So this is representing a hypothetical world without ozone-driven SST pattern effect. And the difference between the two can quantify the ozone's contribution to the SST pattern effect. And here's the percent contribution explained by ozone. Uh, on the on the top panel here shows the net top of atmosphere radiation. Here we used three different Green's functions. These CAM4 and CAM5 and GFDL AM4 uses the prescribed CIs, and the blue curve here it considers the CS changes. And let's first focus on the rapid ozone depletion period from 1979 to 2000. And we can see that this ozone-driven SST pattern changes can increase the radiative cooling to space by up to 2 to 6%. And for the global mean surface temperature response, this ozone-driven SST pattern effect can reduce the global mean surface warming rate by 7 to 18%. So combined, they can lead to a strengthening or a more negative lambda by 8 to 19%, which is up to 0.7 watts per meter square per Kelvin, more negative in lambda. And more importantly is that when we look into the years when ozone starts to recover, this ozone recovery, the ongoing and the projected future ozone recovery could flip the SST pattern effect and transition us into a more warming prone and more sensitive climate in the future. So here's the summary. We show that Antarctica ozone depletion can quantitatively explain a key pattern of SST cooling observed over the past 4 decades if we just consider the robust short timescale response. And this ozone-driven cooling has strengthened Earth's ability to release heat up to space and making the climate up to 20% more stabilizing during the most rapid ozone depletion period from 1979 to 2000. And finally, as Antarctica ozone has begun to recover since the 2000, this stabilizing influence has weakened and it could contribute to a more warming-prone climate and higher effective climate sensitivity. And with that, I would like to thank you very much for your time, and I'm happy to take any questions.
Thanks, Peidong. That's very nice, very clear. We already have one hand raised, Andrew.
Hey, Peidong, that was a great talk. Thank you so much. Could you help me? There's in my mind, there's a little bit of a tension in part of the work where it's like in the beginning, you show, I think it's CSM1 when you isolate the ozone only and you don't get the correct magnitude of the cooling in the Southern Ocean. But then later on, you use PI control models and their internal variability and show that you do get the right or a similar magnitude to what's observed. So does that procedure not work for CSM1 then, but it works for the other models? Or can you help me think that through?
Yeah, thank you very much. Yeah, that's a great question. This is also one of our major confusion when we have the results. The CSM1 it's directly running in the model, so it considers the short timescale response, and it also incorporates this long timescale response, which it could have a stronger deep ocean upwelling. And for our linear regression model trained on these climate model outputs, we just consider the short time scale response. So we neglect this long time scale deep ocean upwelling, and we show that if we just consider this short time scale cooling response, the ozone itself could contribute to a large cooling that is similar to our observation. Yeah, so this is not in contradiction with each other.
And sorry, just to follow up, and is CSM1 one of the models that you look at for the PI control thing as well? I forget that list of models.
Yeah, CESM is I think that's CESM2 Wacom model because we need the interactive stratosphere chemistry.
Cool. All right, thank you. Thanks for the talk.
Any other questions, comments?
Oh, I think
Gavin.
Hi.
Gavin, go ahead.
Yeah, thank you. Interesting. I guess my question here is like all of the models have ozone depletion in them, and they do a reasonable job with the ozone depletion and the ozone hole, and they have pretty much the right trend in the SAM index. So it like saying that pointing to ozone as a contributing factor to the mismatch doesn't really help because all of the models already have that. Am I missing something? What are you suggesting that the model groups do?
Yeah, thank you very much for your question. Yeah, all of these models, they either use interactive ozone or prescribed ozone, but their atmospheric part is pretty good in terms of comparing with observations. But from our analysis, it seems to suggest more of an ocean response. Right now, it seems like the deep ocean upwelling can be too strong. So if we change the ocean parameterization to uh, slow down the deep ocean upwelling in response to surface, for example, SAM changes or ozone changes, this could lead to a more of a cooling in the ocean part in terms of modeling. So I think maybe that's a more ocean parameterization, especially for the mesoscale eddy parameterization, that uh, could lead to more of a ocean cooling.
Okay, thanks.
Thanks, Gavin. We oh, that's still Gavin's hand. So we still have 1 or 2 minutes for the speakers, either Peidong or the two previous speakers. If you have any final comments, questions, this is the time.
If not, I think Vince Cooper wants to
Well,
make a brief announcement as well. Right. You can
I'm
go for
happy
it,
to hold
Vince.
off for another minute, though, in case there are other questions. Thanks, Andrew.
No worries.
I actually have a quick one for Peidong.
mhm.
So you showed that the feedback gets a bit more positive or less stabilizing from the ozone changes. I'm curious about the magnitude of that because a few of us have been looking at that, myself and I think Sen Van Loon and others, and finding a strong effect in the North Pacific as well. So I'm kind of wondering if you combine what's going on in the North Pacific with the ozone influences on the feedback also, does that give you too big of a change in the radiative feedback, perhaps, or whether you've thought about the magnitude of the change in the feedback induced by ozone recovery?
May I clarify the North Pacific? Do you mean the global ozone or just the Antarctica ozone hole itself?
Sorry, I meant for the North Pacific, there's something that's going on that's totally independent from ozone that seems to also be making the feedback much more positive over the past couple of decades. But you've also now pointed out this potential ozone role. So I was wondering if you have those two things both going on, whether that makes sense or whether there's a discord there, in that the feedback trend would be much larger than what we're observing.
Yeah, currently for our analysis, we only consider the dashed region where all the models agree on the science. We didn't consider elsewhere like the North Pacific. But from the three Green's functions models we have, it does show a very large uncertainty. The lambda can range from I think 2% or 7% to 8% to 19% during the most rapid ozone depletion. So there could be a large uncertainty in terms of the Green's function itself. And also here is just considering the southern hemisphere. We didn't consider the northern hemisphere.
Got it. Thanks.
Yeah, Vince, please go ahead. I think,
Okay.
yeah, last chance.
Yeah, sure. Thanks. I just wanted to or remind everyone briefly about the email that was circulated sharing a short survey. We're working on updating the ECS assessment in the spirit of Sherwood Webidal 2020, and we're hoping to incorporate as much community input as possible. So I just put the link to that survey in the chat again, or you can look up the email that was shared over this distribution list, and we hope to incorporate your feedback and are excited to hear everyone's input. So thanks for letting me pub that on this webinar.
Yeah, thanks everyone. Thanks our speakers today. It's been perfect timing, 1 hour. And I'd like to conclude the section today, and we will see you next month for our next section. Have a good summer, everyone.
Thanks, everyone.
Thank you very much.
Thank you.
Yeah, thank you for organizing.